How cool would it be to render 3D graphics in your browser? That's what was on my mind tens of years ago, among other things. But today we can do that, and you've most likely seen it more than once. But how does it work? Let me show you. The cool thing is that similarly to shaders and shader toy, you really don't need any setup or installation. Your browser is more than enough, and the file itself is just an HTML document sprinkled with JavaScript. Notepad will be more than enough, so don't forget to experiment on your own here. This is WebGPU. If you have spent any time dealing with graphics on the web, you are likely familiar with WebGL. While WebGL has several as well, its underlying architecture is fundamentally rooted in the past. WebGPU is the successor, designed from the ground up to bring the core philosophies of modern graphics APIs into your browser. By fundamentally changing how we send commands to the graphics card, we drastically lower the communication overhead and bottlenecks on the main CPU. Plus, we get the compute shaders, which is a native unified API to run massively parallel mathematical operations like particle simulations and custom neural networks. Today, we are laying down the foundation by building the classic hello world of 3D graphics, the spinning cube. And we did it many times before here on the channel. Before we can push geometry to the screen, we need to establish a connection between JavaScript and the physical hardware. In the init WebGPU function, we first check for navigator GPU, because this is a modern standard. We have to gracefully handle unsupported environments, which is why we have a fallback error message baked into our HTML overlay. Assuming the browser supports it, we perform a crucial two-step initialization. Request adapter. We ask the system to find the physical hardware capable of rendering our graphics, whether that is your beefy dedicated graphics card or an integrated chip. By the way, you can clearly see that the GPU is being heavily utilized. And here we have request device. We cannot talk to the adapter directly. Instead, we call request device to create a logical connection. This is our primary interface for allocating memory, compiling shaders, and managing pipelines. You might see a certain resemblance with my video about DX11 programming. Finally, we grab our HTML canvas context using the string WebGPU and configure it by bypassing in our new device and a presentation format. By querying navigator GPU get preferenced canvas format, we ensure the internal memory structures of our pixels perfectly align with what the user's specific display expects. In a 3D rendering pipeline, everything boils down to mathematical grid using normalized device coordinates across the X, Y, and Z axis. Our vertex data holds this geometry as a float 32 array. Notice how we pack this data. For every single vertex, we interleave 8 distinct floating point numbers. The first 4 represent the 3D position, X, Y, Z, and W, and the next 4 represent the color channels, red, green, blue, and alpha. All of them are numbered, just depends how we represent them. This continuous flat block of memory lets the GPU stream it as quickly as possible. A cube has 6 square faces, and since graphics hardware uses triangles, we need 12 triangles in total. That would normally require 36 individual vertices, but if you count our array, we only defined 8. This brings us to a secret of rendering efficiency, the index buffer. If you are my regular viewer, this concept is nothing new, but if not, no problem, it is easy to grasp. Instead of duplicating data and wasting a massive amount of memory and bandwidth, we only defined 8 unique corners. Our index data array, which is unit 16 array, acts like a connect the dots manual. It explicitly tells the pipeline to do a triangle connecting vertices 0, 1, and 2, and then to reuse vertices 0 and 1 alongside vertex 3 for the rest of the face. Easy. Raw data alone does not draw anything. We need to instruct the hardware on how to process those numbers using shaders. Inside our WGSL shaders, we write in the WebGPU shading language. These are tiny, highly specialized programs compiled and sent to execute directly on the GPU's thousands of parallel cores. The vertex shader. The GPU fires this up for every single vertex. It takes the raw 3D coordinates and determines whether that point belongs on your flat 2D monitor by multiplying it by an MVP matrix. It then bundles both the position and the color into a vertex output structure, the fragment shader or pixel shader. Once the shape is rasterized, the GPU rapidly executes this program for every individual pixel inside the triangle borders. Its absolute purpose is to determine the final color. Today, it simply passes the color data through, but in future projects, this exact shader is where we will write complex algorithms for dynamic lighting, shadows, and physics-based materials. Don't forget that if you want to know in more detail every principle we are discussing today, there is a playlist with computer graphics videos in the description. If you look at the device create render pipeline blog, you will see where all this preparation comes together. In older APIs like WebGL, you would swap out shaders and toggle depth testing on the fly. The driver validated those sudden state changes, burning massive amounts of CPU cycles and possibly causing stuttering. WebGPU fundamentally changes this. It forces us to take all our rendering state and strictly bake it into a single immutable render pipeline object before the animation begins. Because the setup is validated ahead of time, the graphics card spends the actual animation loop doing nothing but drawing frames as effectively as physically possible. This is a very modern way of doing things. It might feel restrictive, as you are not allowed to make any changes in the pipeline once committed, but from the GPU's perspective, it is the best way of doing things because it is predictable. We must tell the GPU how to decode our memory buffers. We define an array stride of 32. Since every standard floating point number is exactly 4 bytes, and we grouped 8 numbers per vertex, 32 bytes is the exact mathematical distance the GPU must jump to find the next vertex. We map shader location 0, which is position, to an offset of 0 bytes, and shader location 1, which is color, to an offset of 16 bytes. To get a 3D object to show up correctly on a flat screen, we apply an MVP matrix, as said before, model, view, projection. We use the lightweight GL matrix library to handle the heavy linear algebra. Model defines the continuous rotation, position, and scale of the cube in local space. View. By default, our camera sits at the exact 0, 0, 0 origin point inside the cube. We use look at to pull our camera back and up to coordinates 2, 2.55, pointing it back at the center. Projection. A raw mathematical grid has no concept of human perspective. We use perspective to artificially inject a 45-degree field of view so geometry scales exactly how the human eye expects. Because this matrix changes every frame, we allocate exactly 64 bytes of memory, the size of 4x4 matrix, tagged with GPU buffer usage uniform inside our animation loop. And device queue write buffer constantly overrides this chunk and bind group maps to binding 0 in our WGSL code, which guarantees that every GPU core has the exact same mathematical perspective. The MVP matrix is absolutely fundamental for 3D graphics, so feel free to check out this video. The next step is another crucial one. I like to call it MC Escher style here. By default, the GPU draws triangles in the exact order we submit them. If it processes a back face after a front face, it blindly overrides the screen pixels, destroying the illusion of solid geometry and some spatial sense in general. To solve this, we introduce a Z buffer via a dedicated depth texture. In our pipeline's depth stencil setup, we use a depth 24+ and set the comparison to less. Alongside the visible color canvas, the GPU creates a completely invisible canvas, storing a highly precise 24-bit number representing pixels distance from the camera. Every frame, we clear this texture to 1, which is absolute maximum distance. Before the fragment shader colors a pixel, the GPU performs a rapid hardware level check. Because our rule is less, It only draws the new pixel if its calculated distance is strictly less than the distance already in the buffer. Back wall fragments fail this test, gets discarded, and our cube looks perfectly solid. Do you remember how we programmed a Z buffer from scratch in the previous video? How much easier are things when everything is prepared for you and we can just use it out of the box? If we stopped here, you would just stare at a blank screen. Kinda disappointing after all this setup. What we need now is a heartbeat. Down in our request animation frame loop, the real low-level communication happens. Because your CPU and discrete GPU are separate asynchronous processors, we cannot just yell individual draw commands over the motherboard bus and expect instant execution. The overhead would cripple performance. Instead, we write our instructions down ahead of time using create command encoder. Think of it as a tightly packed memory buffer where we write the recipe. We configure our render path, clearing the background to a dark Tailwind CSS Slate 900, bind our pipeline, attach the uniform bind group, plug in our buffers, and issue the raw indexed. Up to this exact line, absolutely nothing has happened on the physical hardware. To actually generate the frame, we call finish on our encoder to lock in the recipe and drop it into device queue submit. This puts the commands into the GPU's execution inbox, allowing the hardware to execute them at maximum silicon speed, while our JavaScript thread moves on to the next frame. There is one thing that might be bothering you. If you look closely at our spinning cube, you might notice a diagonal seam across the squares where the color gradient suddenly shifts. This is not a bug. It is a manifestation of our hardware logic. The GPU is independently interpolating one triangle between three shared corner colors and the adjacent triangle between a slightly different combination. That visible seam is the literal mathematical boundary where rasterization switches from one triangle to the next. Fixing this would require 24 distinct vertices instead of 8. But here we have a classic low-level trade-off between memory bandwidth and visual fidelity. And there we have it. By writing a single HTML file and a little bit of JavaScript, we successfully requested a hardware adapter, packed interleaved memory, compiled shaders, calculated perspective matrices, and orchestrated an incredibly fast render loop. That will be all for today. If you like what you saw, hit the subscribe button, consider leaving a like or comment, or even a membership if you want to support the channel. This cube is the hello world of modern graphics. If you want to understand a little bit more of the math behind it all, check out this video. I hope you learned something. Thanks for watching, and ciao!